Hi, this is Ian from Johns Hopkins University. I'll be presenting our work, Range Avoidance and Remote Point, New Algorithm and Hardness. This joined with Shentang Huang from University of Science and Technology of China and Xin Li from Johns Hopkins University. Here is the outline of today's talk. First, I'll introduce the motivation for this work, and then I'll overview our results. Third, we'll get a little bit into how we prove our equivalence results. And finally, I'll introduce our algorithm for NC0 avoid. Our motivation for this work, in a word, is to study explicit construction problems via range avoidance. So what's a range avoidance problem? It's given a circuit G from n bits to m bits with m larger than n. Try to find a string y in the codomain that is not in the range of G. And people usually abbreviate this problem as avoid. This problem captures a wide class of explicit construction problems like Ramsey graph, expanders, rigid matrices, and Hart functions. Different genres of algorithm like pseudo-deterministic algorithm or polynomial time algorithm with an NP oracle for avoid with appropriate parameters usually leads to circular bounds. Since the problem is quite central to, is connected to quite a lot of central problems of interest, there has been a bulk of recent developments. The first kind of results is the equivalence between algorithm for avoid and circular bounds. This was first established by the work of Oliver Corden in 2021. In this paper, we also extend such equivalence results. Second, there is a long line of work studying the implication from algorithms of avoid and also designing algorithm for avoid. Third, there has been, so the study of avoid and algorithm for avoid has also led to improvement over long-standing circular bounds problem and also data structure lower bound problem. Lastly, people have been studying the hardness of avoid against deterministic algorithm or non-deterministic algorithm from using techniques from cryptography, and this line of work are usually intimately connected with proof complexity. Actually, in the same conference, there is another work on the hardness of avoid and its connection to proof complexity. You're very welcome to check that out as well. As you see, avoid is intimately connected with explicit construction problems as well as circular bounds. Okay, now I'll give an overview of our results. The kind of equivalence theorem that we prove is as follows. We show that for any constant circuit classes containing AC0, there is a polynomial time algorithm with an NP oracle for C avoid with stretch, polynomial stretch, if and only if there is an almost everywhere exponential size C circular band against e to the NP. This extends Cartan's original results from P/poly to circuit like AC0, ACC0, TC0, etc. We also show a near equivalence, and here we'll need a parameter delta, which can be any constant from 0 to 1. We show that there is an almost everywhere near maximum size formula lower bound against e to the np if and only if there is a fp to the np algorithm for NC0 avoid with 2n stretch. This is not an if only. This is not an if only if theorem. It's that if you can show that there is an almost everywhere near maximum formula size lower bound against e to the np, then you can then this will give you an fp to the np algorithm for NC0 avoid with 2n stretch. On the other hand, if there is an fp to the np for a slightly smaller stretch for NC0 avoid, that is n plus n to the delta stretch, then we will be able to show an almost everywhere near maximum formula size lower bound against e to the np. We also managed to extend the original results between avoid and the worst case hardness to remote point and average case hardness. The second set of results are a new algorithm for low depth avoid, specifically NC0 avoid. We give the first sub-exponential time algorithm for NC0 avoid with any locality for for any superlinear stretch. This algorithm was later slightly improved by the work of Goswami, Liu, and Yuan. It is worth noting that a peer of recent work by Corton, Pitasi, and Pagliazzo, as well as Goswami, Liu, and Yuan, improved the polynomial time algorithm for NC0 avoid to quite a small stretch. We also gave a faster than brute force algorithm for NC0 avoid with minimum stretch. Okay, so now let's see how we prove the equivalence results. Um, so the forward direction is that if you have an algorithm for avoid, then you would get a circular bound. This direction was actually largely established by the work of Aaron Sassanam and Wang, as well as Chen Huang. So the main work of this paper is to show the reverse direction, and the technique that we'll be using is called generalized Q-array geometry. So the original technique used was binary geometry, and the circuit there has stretch 2m. Now we extend this to Q-array geometry, so you should be thinking of our circuit as has stretch qm, and for each of the small blocks here, you should think of there will be a circuit C at any blocks here. More specifically, how we construct this geometry is as follows. Given a circuit C from n bits to qn bits, and the height of the geometry we set to k, and the parameter L just characterize the output length of the geometry, we construct the circuit tree as follows. We build a valued perfect Q-array tree of height k, and let ij denote the jth node at level I. It's easy to say that the h child of ij node is node I plus 1, qj plus h. And the value of node ij is denoted by vij, and we set v00 to be x. And with this initial setup, we can compute the value of any the value of vij for any ij by recursively computing it. Specifically, if we have a value of vij, we can compute the value of its children, and assign the appropriate block of the, say, cvij which equals to y, assign the appropriate block of y to the appropriate child. And finally, the output of the geometry is a concatenation of the values at the final layer of the tree. The key property that we'll be utilizing is that the circuit complexity of the geometry is small. Actually, it's linear in the size of the circuit C and the height of the tree. So what we prove in this work is that if the C circuit is from a class C, which contains which are constant depths and bounded Fein circuit classes, which contains AC0, and if we further guarantee the height of the tree is a constant, then we will be able to show that the C circuit complexity. So the circuit complexity of the output of the GGM tree is in most O as C times K. Moreover, this can be computed by a circuit from the class curly C. Lastly, the same conclusion would be easily adapted to formula complexity. Okay, so now we know how to construct this GGM tree, and we know that the output of the GGM tree has small curly C circuit complexity. Then we can use an F, which is outside the range of the GGM tree. This can be just a circuit that cannot be computed by curly C circuit of particular size. That is, if there is a circular band, then definitely outside the range of the GGM tree, we can use that string to traverse down the GGM tree and find a string Y not in the range of the C. And we're guaranteed to be successful, as if we're not successful, then we would be able to show that F has small circuit complexity, which would be a contradiction. You may wonder if this technique can be directly adapted to remote point. It turns out not. So here is a simple counterexample. Also consider the binary case in your circuit C is of stretch 2n, and you have an average case Hartree stable Y, and you divide it into blocks of equal size, 2 blocks of equal size Y1 and Y2, and you consider the GGM tree whose output length is 4n, and so it has height 2 and arity 2. And assume that you're not successful in finding the remote point. So at each level, you would be able to find a pre-image that is close to the specific string that you have in hand. That is, you would be able to find an x1, which is close to which applying on C, that is cx1 is close to y1, and you'll be able to find an x2 such that cx2 is close to y2. And again, you will be able to find an x such that cx is close to x1 concatenated with x2. And now you try to derive a contradiction from this x. So now set the cx to be x1 prime concatenated with x2 prime. But it's not clear like how close is cx1 prime with regard to y1 and how close is cx2 prime with regard to y2. That is, we cannot conclude anything about the distance between y and the output of the GGM tree on x. So this is not clear how this leads to a contradiction. So our remedy for this is that we apply something like a list decoder on the array intermedia layer of the circuit C. And so more specifically, given a circuit from n bits to m bits, and we need an appropriate least decodable code. And we still set the height of the GGM tree to be k, and the final parameter L is just the output length of the GGM tree. And the construction is as follows. So we pad each circuit C tilde. That is, we pad log L bits to both the inputs and the outputs. Here, L is the least size of the least decodable codes. And then we build a value perfect Q array tree just as before, and let ij denote the J's node at level I. And again, you can easily compute the index of the H's child. And the value is set same as before. But note that here x is of length n plus log L. So at each node ij, we compute the value of y. So first apply C tilde on Vij, and then apply the selector with the list decoder and obtain y. And then you divide y into h+1 blocks of length n plus log L bits and assign it to the appropriate child. Here, this select decoder circuit is that you would regard C tilde Vij as the code word concatenated with some log L bits. So if you directly apply the least decoder on the encoded code word, then you would get a list of message strings. But then you have this log L bits to help you select a particular string from this list. So the output of selector decoder will be of length the same as the length of the message, of a single message. Okay, so with this adaptation, we would be able to modify the reduction correspondingly and do the like traverse down the GGM tree to find a remote point for C. So and now I'll introduce the algorithms for NC0 avoid. Our algorithm for NC0 avoids leverage a key combinatorial fact about the structure of the NC0 circuit. So basically you can think of the NC0 circuits as a bipartite graph where the input bits is on the right-hand side and the output bits is on the left-hand side. Since this is the NC0, it's the NC0 key circuits, and you know that it's like a left regular bipartite graph where the degree is K. And so we'll need the notion of a disperser graph, which is another kind of bipartite graph, such that for you have this kind of expansion guarantee that is for every set X of a subset of from one side of a particular cardinality, you're sure that its neighbor side is larger than a particular threshold. And so we'll use known lower bounds on bipartite disperser graph and to derive some structural results for the NC0 circuits. So you have, say, you have a graph which is a D left regular bipartite graph, then and you set its particular expansion property characterized by the parameters, and there is some bands on the degree of the graph. And if you translate this G to an NC0 circuit in our setting, and you set the input, the number of input bits to n and the number of output bits to be just any superlinear size, then we can derive an upper bound on the set, on the size of the set that you would expect to see the expansion. So that means just for any set of if you look at any set of cardinality larger than K0, it doesn't have such expansion property. And so if this circuit doesn't have this expansion property, then we're able to argue that it contains a smaller instance of NC0 avoid. That is, there is a subset of the output bits whose neighbors have size smaller than this set of output bits. So this would constitute a smaller instance of NC0 avoid. And then we can just solve this smaller instance by brute force. And so we would be able to find a string not in the range of the smaller instance, but this string can be extended to a string in the codomain of the original instance just by assigning the remaining bits to be arbitrary in bits. And this also constitutes a solution to the original NC0 instance. So in general, if a graph is not a disperser, then we can find this smaller instance with ease. So the hardest case is this the case when this graph is a disperser, but still there is this lower bound on this disperser that we can leverage. Okay, so more specifically, here's our algorithm. First, we search over. So we already know, since we already set up the parameters of the circuit, then we know that there is a subset of the output bits, which would constitute a smaller instance of NC0 avoid. Then we just brute force search over all such a subset as with a property that its neighbors has size smaller than itself. And then we can just enumerate overall its input bits and find a solution that is not in the range of it. And then we can just assign arbitrary values to the remaining output bits of the original instance, and this would constitute a solution. So in this algorithm, we are actually able to find a tons of strings that is not in the range of the NC0 instance. Okay, so that's the end of my presentation. Thank you very much for listening.